Alright, hello everybody. My name is Muhammad Afzal. I am a senior in Niles West High School, part of the SIRS class where we do student research. For my video project, I'm going to discuss what exactly data analysis should look like and what values are essentially the norm for the IJAS Science Fair and other science fairs that look at statistical tests and or common data analysis techniques to obtain accurate conclusions in your experiment. So I'm going to be specifically looking at 95% confidence intervals and what exactly they are in terms of data analysis. And this also goes into standard error as opposed I'm so sorry, what am I typing? As opposed to standard deviation. Because standard deviation, which I will go into later a bit more, is basically just a representation of the distribution of all your values, whereas standard error takes into account your sample size. And with this, I'm also going to talk a bit about how to use Google Sheets in terms of graphing, and then how to relate that into statistical tests that you can use later on, mainly talking about the normal distribution. And these are a bunch of different topics, but if once we go through them, it'll make a lot more sense. So again, I'm very sorry if I misspeak or if I type incorrectly. So first things first, we're going to look at a couple, just some data here. We have 3 cars, A, B, and C, and there's 3 separate days, 1, 2, and 3. Now, the cars A, B, and C are 3 independent variables. Just assume that there are 3 different cars. And day 1, 2, and 3 represents 3 different days in which these values are just represented as miles per hour. That is the units we're working with. So first things first is I'm going to make a graph of this. And now you see how car A, car B, and car C in this bar graph right here does not have 1 bar per independent variable. And the reason is because we have multiple values per car. And so we need to take the average of all 3 days to find out the amount of miles per hour that that car rode on average. So in order to do that, first we create what is it called? A table for the summary data table that basically relates the independent variable, which are our car A and B and C. So we're going to have our independent variable, and that'll be for cars A, B, and C. And then we have our dependent variable. I'm going to write that up here. Dependent variable. And that will consist of the just total number of days, or overall days. Because essentially what we want to do is we want to take the average of each independent variable and see how that relates with one another. So in order to do this, you say equals average in all capital letters. You click on the average function that's listed, and when you click that, it'll give you this weird box. Essentially what this box is saying is that you're going to plug in 2 different values. There's going to be value 1, comma value 2, comma value 3, and it will take the average of every single value put in those parentheses. Now, we could do something simple as for example, if we're taking the average of car A, and car A is over here, we could take the average of 13, comma 12, comma 11, and the average of that is 12. But this doesn't work if you have multiple data points. So what we do is that we look at the coordinates for that specific data value. We have C3, so we write C, capital C, 3, and then colon. Colon represents a distribution, or like dragging over your mouse a certain distance. So we want to go from C3 to E3, and see, that gives us the same answer as 12. So, and it highlights which sections of the data it is actually going to take the average of. Another way to do this, if you don't quite understand the numbering or the coordinate process, is you can, once you have the average in parentheses, you could drag over the specific data points that you want to take the average of, and you take the average of those values. Now that we've taken the average of one data set, we press enter, and the number is then popped up. Now you could write the same function for each one of these independent variables, but that's a lot of work. So what you do is there's this little blue dot right here, and you get this plus sign that pops up. That means that you're adding whatever function that exists within that cell. We can see up here in the function area that it equals average of this. If we take it one down, now your average number changes here, because this accounts for the other independent variable. This car B is taking the average of C4, D4, and E4, and we get that value. And now we're going to do the same thing for the last one, and we get a different average value, which all makes sense. Now you have a bunch of repeating decimals here, and in order to get rid of those, you highlight over all of your dependent variables because you want to standardize or make sure that you have the same number of significant figures for each of your values per independent variable. You're going to go to the decimal place value, and you're just going to decrease decimal places, and then you increase by 1 and by 2. I do a standard of 2 just because it is much better to recognize in the hundredths area for data points, but depending on your data you may or may not want to change that. Now we have our average values, and let's say we graph this now. So we're going to just take this and graph it. Right now it's a pie chart, but we're going to make it into there. There you go. Now you have one independent variable, just 3 different cars, and you have different average values for each one of them. Now the problem becomes is that all of these are the same exact color, and in order to combat that, you have to separate these different bars into different series. And so in order to do that, you have to essentially rearrange this average graph. What you're going to do is you're going to have car A, car B, car C, and you're going to have your average, and you're going to have it so that now these values right here, if you write 12 and 16.33, that works. But what if you want the exact value? So if you click equals and then just the cell you want it to equal, it will automatically give you the answer, and it will change it if you change the original cell. So it's much more efficient to write the equal and then the cell coordinate. So you press enter, and this way you have to write this, click it, enter, equals this, I5, this is I5, it's yellow highlighted, so we want that value. Now we're going to take the chart of this. Now you see how it's the same exact graph, but there's something different. Over here it says overall days average versus independent variable, whereas here it just says average. That is because in this we include the word independent variable. Now if we go in here and we edit the chart and we switch the rows and columns, there's no data, because you're essentially telling Google Sheets that you have no dependent variable, which is incorrect. So we go back to there, but if we click it here, we now have 3 different colors, meaning 3 different sets of data. Our 3 different colors would represent our independent variable, and then our dependent variable would be shown on the y-axis. This is technically a histogram. It is not necessarily a bar graph because you are not comparing 3 individual bars, but it is a good representation of how to compare 3 different series in Google Sheets. Just to remember, you would have your dependent variable values on the horizontal portion, the vertical portion, and then horizontally you would have your independent variable components. And then once you go there, you click switch rows and columns, and you should get these 3 different values. Now we get to error bars. Error bars are a difficult concept. Everyone has learned over the years that standard deviation is the way you get your error bars. Error bars means that little segment that's surrounding your average value that tells you the error to that specific value. What exactly is standard deviation? Let's assume you have a normal curve. A normal curve is basically where there is one single peak, and as the data skews away from the mean, we're going to call this Greek letter mu. As the data skews away from mu, the probability of getting that data becomes smaller and smaller. Now, here's what their situation lies. If you do one standard deviation of this data, you will essentially get this much of the normal distribution. And this is roughly 50%. Now, this is a problem, because you're saying that for every single time you do a experiment, that the standard deviation you are using to count as error only accounts for 50% of those samples. And the other 50%, your mean could be on the outer skirts of the normal distribution. That is incorrect. We want to account for the most error possible to obtain a conclusion that is well supported. So in order to do that, we do not simply look at standard deviation, because standard deviation, which is important to note, refers to the distribution of values. And so in that manner, having just the standard deviation will not necessarily explain whether or not your data point is accurate or whether or not it has much error involved within it. So we look at standard error. Standard deviation is predominantly denominated as SD. That is standard deviation. Standard error is called SE or SEX or SEM. Any of these are noted as standard error or standard error of the mean. And so what standard error of the mean does is it accounts for your sample size. Let's say, for example, in our little experiment here, we had one independent variable, one dependent variable, but multiple data values. And so our sample size in this case was 3, because we had 3 separate days. And if you consider, let's say, an entire population of cars where we go into the millions and billions of amounts, standard deviation becomes more appropriate. It deals with the distribution of a population. But standard error accounts for the sample size. In our experiment, we only have a sample size of 3. The amount of error that exists within that becomes much more possible. And so we want to consider the sample size when discussing error. So what we do is we say that the standard error is equal to the standard deviation divided by the square root of n. And n equals the sample size of our experiment. And the reason this is important, actually I've quite honestly explained why this is important, but I'll reiterate that if you do not consider the standard error, meaning consider the sample size, then you are basically assuming that your experiment represents, if you were to do this for a whole population, and there is no physical way that any experiment is done with the whole population. So you basically almost always will have to use this standard error formula unless you know specifically what the standard deviation is for the entire population of whatever dependent variable group you're using. And so one thing to note is that this standard standard deviation graph that I've just shown you is a bit flawed. So we have standard deviation right here. I'll write out standard deviation. So this is standard deviation, but then we also have standard error. Standard error has the same curve because all it is representing a sample, not the population. I'm sorry about this horrible curve. You also have your mean on the bottom here, that's mu. But in this case, one SE refers to, I'm sorry, this is not 50%, this is 67%. Sorry, that was my bad. But going back here, you have still the 67% you're referring to when talking about one SEM. And so we've accounted for the sample size. Now we have to account for a majority of this distribution. So what do? We just take a larger range. The SEM refers to values that go beyond the mean. So for example, if let's say your mean is 20, right, and your SEM is 5, that means that your maximum value would be 25 and your minimum value would be 15. So this goes from 25 to 15, or another way to write it would be 20 plus or minus 5. Now if we increase this value right here, which represents our SEM, then we basically account for a larger range, meaning we account for more of this distribution. So let's say, for example, make it 10. Now if you make it 10, so it would be 20 plus or minus 10, your values change from 30 to 10. Now that you have a larger range, you account for more error that is possible, and thus your conclusion is based off of more reliable facts. So if you do one SEM, it usually is 67%. But if you do two SEM, it is approximately 95%. This means that if you were to take many, like so many samples you can't imagine of the data that you are collecting, the 95% of the samples will contain the actual true mean value of your experiment. You can be sure that 95% of all those samples will actually have the value that you got in your experiment. And so that's what we're gonna have to do. We have to calculate for the 2 SEM to account for our error bars. So first things first, we have our averages over here. Actually, I'll use this graph considering we already incorporated it here. Averages over here. First thing we want to do is we're going to account for our standard deviation, or in this case, STDEV. Ignore what's happening to the graph. That's just because of Google Sheets trying to relate numbers in some way. So our standard deviation, it equals STDEV of just, now if we click this value right here, what does that tell us? That tells us the standard deviation of one single value, but we don't want that. We want the standard deviation of the distribution of values, and so we highlight over the specified area. So this is car A, so you want to drag over all of car A, and then we close the parenthesis and press enter, and we know that the standard deviation of that car A is 1. Now we're going to do the same thing for this STDEV. Now you see just this suggested based on cell I9, that's basically Google Sheets telling you, hey, I have this formula in I9 and maybe this is what you're looking for, but we don't want that. That's telling us to look for this data, when in reality we want C4 to E4. So we're going to go from C4 to E4. Car B matches with car B, close the parentheses, press enter. And now this last one here, you're going to do the same thing again. STDEV, you drag over the selected cells, and you close your parentheses and press enter. Now that we have this, we're going to calculate our SEM. So I'm going to call this SEM. So this would equal your standard deviation, which is this value right here. We want to click this specific cell, equals this divided by, so that would just be the slash symbol, the square root, which is denoted as SQRT. Just click this SQRT right here, and then you divide by the square root of 3, because your sample size in this experiment is 3. And now you do the same things for the other ones. So it equals J9, which is this, divided by the square root of 3. And now we can drag this over here and we get the same value. Now on the graph over here, we see that there's more and more bars coming up. This is not necessarily true. we're going to be adding error bars, not more bars. So I will explain more about this later. Now we have to get 2 SEM, or 95% confidence intervals. And I will go into, I already explained confidence intervals, but I did mention them by name. I'll go back and explain that as well. To do this, you just do equals, and then 2 times, which is the asterisk key, and then the value, or the SEM value for that specific group. So do 2 times 0.577, or just click the cell, and you press enter. That's all you do. And you can drag it this way, because the suggested is just going to confirm that, hey, you want to multiply by the 2 above it? Okay, sure. So then it's going to go here. 2 times 2 is 4, so that roughly makes sense. And then 4 times 2 is 8, so that roughly makes sense. So now we have our 2 SEMs and we have our averages. How do we connect them? We go and we edit the chart. We're going to customize the chart. Well, actually, before we even go do that, what we're going to do is, we see this data range value right here. And if we click it, it tells us that it's going from H7 to K11. So H7 is right here, and then K11 is down there. Well, we don't want that. We just want these values. So we do that, and we get our averages back. Now, we need to add these 2 SEMs for error bars. We're going to go here. We're going to go to series. We're going to go to the specific series we want to apply the error bar to. So car A. Car A, we click the error bars button. And no, we do not want it as a percent. We want an actual constant number, because the units for the error bars as well as the averages are the same. Go to constant, and now we type in our constant, which in this case is 1.15. I'm going to round to the nearest thousandth. So nearest hundredth. So 1.15. See, and that's our error bar. That little blue segment, that represents that 95% of all errors accounted in that little error right there. Now we're going to go to, you also want to click data labels just so that you can see where your average is. It's a bit easier to notice. So now you have 12. We're going to go to car B now and do the same thing. Error bars. We change the percent to a constant, and then we change that constant value to what matches with the 2 SEM at car B, which is 4.37. 4.37, approximately. And we're going to go to car C. Oh, sorry, forgot the data labels. We go to car C, and we see error bars, constant, 8.35, data labels, and there we go. We have a bar graph that represents 95% confidence intervals as our error bars. And we know that this works according to the normal distribution. The normal distribution explains to us that 2 SEM represents the amount of error encompassed in 95% of the normal distribution. I keep on saying normal distribution, but I'm going to reiterate what that exactly means, just so that you guys are not confused. The normal distribution is basically me saying that, let's say we have an average of 20 again, right? This is our average. And we write this again, draw the normal curve. The center of this graph is 20. That's the mean. This is the most likely outcome of your experiment. Now, you have a range of data values that can go this way, and a range of data values that can go this way. That represents your range of values. Now, what these ends are, we don't know, but we can figure that out using our error. Error tells us how far away we are from this 20 value. If we were to do the experiment again, would we get a number greater than 20 or less than 20? What is the probability of us getting that answer? So the 95% confidence interval tells us, all right, let's just say our SEM is this 5 number right here. So we're going to take, all right, so, sorry, we're going to go right there and right there, this is going to be 20 plus 5, so it's 25. And this is going to be 20 minus 5, which is 15. Now, you'll see, like, oh, isn't this 0? Yes, that is 0. But just because that is 0 doesn't necessarily mean that, you know, this is increasing incrementally. These values are not standard. You're not going from 15 to 16 to 17. There could be a huge jump from 15 to 16 to 17 to 18 to 19. So do not worry about how the data values are arranged rather than what they actually are. So this represents 95% confidence. That means that if you were to do the same experiment again, you are 95% sure that the value you are going to get will be between 15 and 25. There is an off chance that, because there's still 5% left over, there is an off chance that you can get a value above 25 or less than 15. So if you get there's a 5% chance of getting a value that is greater than 25 or less than 15. And so when you go in your conclusion, you have to make sure that you at least mention this portion, because that is what is necessary to identify error. You say we are 95% sure that the value exists between these two values, but there's still 5% chance that they don't. So more data needs to be conducted so that this 5% chance becomes less likely of an outcome. I believe I have went over everything that I was supposed to. If there are any comments, questions, concerns, I would go on to Khan Academy. This is not a sponsored video, but Khan Academy has multiple videos on statistics and how you can apply them in a science area. Just a little quick tidbit though for those who want to go more into this. A normal distribution only occurs if you have mean values. But let's say you're looking at values over time, or you're comparing two separate values. You can't necessarily do that anymore. I'm going to color this white. It's taking me a while. Alright. There are other tests out there that represent t-distributions. So right now we're looking at specifically the normal distribution, which is denoted as n. There's also a t-distribution, and then there's also a chi-square distribution. And depending on what your data looks like, you want to use one of these three. However, if you do not have a normal distribution, a t-distribution, a binomial distribution, or a chi-squared set of values, then you want to look at the ANOVA test. The ANOVA test is able to compare values that do not exist necessarily within a normal distribution. If you are doing a biological project, this becomes very important for you, because not all of your values are going to be dependent on just one independent variable. There's other factors. So the ANOVA test allows you to consider other factors and still get a quote-unquote value of 95% error or something to that degree. So looking and understanding these four concepts is important in identifying what data analysis to use in your project. And so if there are any questions, look over the video. I believe I have covered everything. If your graphs do not work the way that you want them to, you can go on YouTube and there's more Google help from Google themselves. And good luck with your project, everyone. I hope you do well.